Assalamu alaikum, everyone. This is Shishakil, and today we're going to discuss something about A2 physics, and the topic is gravitational field. And inside gravitational field, today we will discuss something about the gravitational force, Newton's law of universal gravitation, and the satellite system of Earth. Okay, so first of all, we know that the gravitational force between the point masses? Well, the gravitational force, as you know, is the attractive force, and it exists between every two objects, regardless of their mass or position in the universe. And this is a weak force among all the natural forces, and the force is acting at center of gravity of the object. Well, a term point mass is coming. So what is point mass? If an object is having all its mass concentrated at its center, then we say it is the point mass because we have to measure the distance from that point at which the whole mass is concentrating. And it is also assumed that all the gravitational field lines are terminating or intersecting at center of that object. So let's say if this is planet Earth, so then we can say that uh, all the gravitational field lines, if you plot, they are they are intersecting at one point, which is the center of that planet. So that's why we can say that Earth is a point mass because its mass is assumed to be located at the center. Why? Because all the gravitational field lines are intersecting at that point. One more concept about that is if there are two objects which are far apart from each other, such that distance between them is greater than the radius of the bigger object, then we say that those are point masses. And the example are Sun and Earth. So as both are separated with the distance that is greater than the diameter of the Sun, that's why we say that these two are the point masses. Okay, so talking about the Newton's law of universal gravitation, Newton said that if there are two objects, suppose this is object A and this is object B, and the distance between their centers is r. So Newton said that object A is going to pull object B towards itself, and object B is going to pull object A from its center with a force Fp. And Newton said that these two forces are actually equal according to his third law of motion, and this is equal to gravitational force, this gravitational force. And of course, as they're vectors, so they have opposite directions, so you have to assign a negative sign with one of them, but their magnitudes are equal. So Newton said that uh, the attractive force is directly proportional to product of masses and inversely proportional to square of distance between their centers. Like the gravitational force is directly proportional to product of masses. It depends on masses of both objects and it depends on the distance or the separation between their centers. So this R is the separation between their centers. Combining both of them together and then assigning a constant over there so we can get this expression. So this G is actually universal gravitational constant. Universal gravitational constant, and its value is 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. Okay, what is the significance of this law? Well, it's about to calculate the force between the two masses. So it says that both objects will exert the same amount of force on each other regardless of their size or mass. Gravitational force is negative. This shows that it is attractive. So actually, it's like gravitational force expression is this minus G capital M small m over r square. So this negative sign with vector, like gravitational force is negative. So gravitational force is a vector, so it shows the direction. And the direction is such that this force is only attractive. Like the direction is always towards center of the planet or the object that is exerting the force. So during quantitative analysis or finding the magnitude of the gravitational force, you simply ignore the negative sign because that is part of the direction, not part of the magnitude. And the value of g, I already told you. Distance r is really important because it is the distance between centers of two objects. This is point to be noted over here, that it is the distance between center of the objects, not between the surface of the objects. Okay, let's do an example. Suppose there is Earth, and well, just bear with the rough drawing over there. This is the Earth, and its mass is given 6 into 10 to the power 24 kg, and its radius is 6,400 kilometer, which in meters is 6.4 into 10 to the power 6 meter. So a mass is placed on the surface of Earth, and what you have to do is you have to find the gravitational force between Earth and that mass. So obviously you will be ignoring the negative sign over there because you're going to find the magnitude of that. So G is 6.67 times 10 to the power negative 11. Mass of Earth is 6 into 10 to the power 24. Mass of the small object is 50 kilograms. And the important thing, distance between center of the Earth to that object is 6.4 times 10 to the power 6. And don't forget to take the square. And this will give you the answer. Hold the calculator in your hand, which I'm not having at the moment, so you can get your answer. Okay, similarly, you can try this question. Well, for this question, what you have to do is um, there's a satellite which is at some height, which is 465 kilometer, and along with the radius of Earth already given to you, which is 6,400 kilometer, you have to find the gravitational force between the satellite and the Earth. So again, you would be using the same equation, but this time the only thing is that this r is actually distance from center of Earth to the ISS, right? So this is r. So this is like radius of Earth plus height above it. So radius of Earth is 6,400, and the ISS height above surface is this. So you're gonna add them and you end up with this. I hope my maths is good because I'm not having the calculator in my hand at the moment. So this is the radius. So what else you need to do to convert this kilometer away? So that's why you will use the same thing, and you will use this value at place of r, and be careful with the prefixes. Okay, let's do the graphical analysis of the gravitational motion. That's quite simple. The product of masses is taken along x-axis and the force is taken along y-axis. So we can say that as both are directly proportional to each other, so it would be a straight line through origin. For second, it's the inverse square law. It is Fg against r. So if you increase r uh, twice, the gravitational force is going to decrease 4 times because this is r square and you have plotted r. It means it would be a very steep fall over here just because here is r square and you have plotted r. The next thing is again the same, but this time you have plotted r square. So it means that if r square decreases 2 times, then force will increase 2 times, or vice versa. Or you can say the other way, that if r square is increased 2 times, then this force gonna decrease 2 times. Why? Because now r square is plotted over there. So it means that this graph would be less steep. So the only difference is that the top graph was more steep, but this graph is less steep. Okay, so let's move forward now. Okay, let's get to the new topic, and that is just Wait for a second. Okay, so now we have to apply Newton's gravitational law on the circular orbits. Sorry for some pause. The slideshow was what not working actually, and hopefully it will work in a better way now. Okay, so we have to look for how Newton's gravitational law is applied to the circular orbits. You know what's the orbit? Orbit is the path along which a planet or a satellite moves due to the strong gravitational pull. Let's say Earth is having its own orbit around Sun, Moon is having its own orbit or path of rotation around Earth. So the orbits are caused because of the strong gravitational pull of the planet or star at the center, and then the other nearby masses start moving around those masses. So the most planet in the solar system have orbits which are nearly circular. The orbits of artificial satellites, the man-made satellites around planets are also circular. So Moon has a circular orbit as well. Actually, they are elliptical, but for sake of ease in calculation, we assume they are circular. Okay, so the circular motion idea can be related to the centripetal force and the gravitational force between the two masses. So we say that if anything is moving around circular track, then the gravitational force by the object which is at center of the orbit is providing the centripetal force. So, well, the terms that will be used in the satellite motion will be the orbital radius, orbital speed, time period of the satellite, and the angular speed of the satellite. Well, what is the satellite? As I told you earlier about the orbit. So if anything is moving, any mass is moving in the orbit, due to the gravitational pull at due to the object at the center, then that mass is called a satellite. And there are two types of satellite. One is natural, which are planets. Planets are the satellites of sun, and moons are the satellite of planets. And second are the artificial satellites, which are man-made satellites, and we use them for communication, for military surveillance, and for weather forecasting as well. So, well, in the diagram, you can see that Sun is at the center, and this is a planet. Its mass is small m, Sun's mass is big M, and its orbital radius is r, and it is moving with the speed v, and the planet will take time t to make one rotation. If this is Earth, then it takes 365 days to complete one rotation. And as the Earth is moving around Sun, so it will have its angular velocity as well. That's why I told you about these things that we're gonna study for these satellites. Well, this is a satellite, and you can see that this satellite is moving around Earth, but it is moving along the equator because this line is above the equator, and the satellite remains fixed at one point. And this seems, what region is shown on the map? It's, I guess, South American region. Yeah, it's a South America. So the satellite is having a fixed position. So that's why it is a geostationary satellite. Well, there's another satellite as well that is changing its position with respect to Earth. So it's going all around Earth between North and South Pole. So these are called the polar satellite. So this is the example of polar satellite, and this is the example of geostationary satellite. Well, let's look upon geostationary satellite, a satellite that orbits around Earth so that it passes over a fixed point on the Earth's surface at the same time each day is called geosynchronous. Synchronous means that its time period and frequency is same as that of Earth. So this is called geostationary satellite. Geostationary satellite. Okay, so you can see in the diagram that it is at the fixed position. It is over the South American country. So at all times of the day or the year, it remains over that. So that's why we say this is geostationary. Geo means Earth, stationary means static. It means that with respect to a point on Earth, it seemed to be at rest. Why? Because it is orbiting around Earth at the same speed as Earth is spinning around its own axis. Keeping in mind, this is north, this is south, and this one is equator line. Okay, so this is geostationary satellite, and well, what are the features of it? So first of all, the orbit of these satellite is called geostationary orbits. Then these are above the equatorial region. This is above equator only. And the satellite of these orbits are geosynchronous. It means they have the same time period as that of spinning of planet about its axis. So let's say you know that the spin time period of Earth about its axis is 24 hours. So it means that the geostationary satellite around Earth will take 24 hours to complete one rotation. The satellite orbit west to east, because Earth is spinning west to east, so they spin in the same direction. So they are always going from west to east around the Earth. And then these satellites, well, need not to be traced. It means they remain at same point with respect to a point on Earth. Like here, it's on above the North America, so all time of date will remain over there. And what are their uses? These are used for the communication and for weather forecasting. Well, the facts, the time period for the geostationary satellite should be same as the spinning time period of the planet or Earth. In case of Earth, it is 24 hours. It is located above the equatorial regions. This is very important. And their approximate height is 36,000 kilometer above the surface of the Earth. Now let's look upon polar satellites. So polar satellites revolve around Earth in a north-south orbit, passing over the poles as the Earth spin about its north-south axis. So you can see here that this is the North Pole and this is the South Pole. This is the spinning axis. Earth is actually spinning west to east, but these satellites are moving between north and south. So that's why these are called polar satellites. Well, the polar satellites have the variable orbital radius, which are not fixed. The lowest orbit is 150 kilometer, just 150 kilometer above the surface of Earth. And then these satellites have different time periods because their height vary. And these are used for communication, for GPS, for military surveillance. And then the group of satellites are used to communicate between 2 points of Earth. Why? Because they are moving too fast. And a very interesting thing is that the time period for this satellite, which is 150 kilometer above, like it takes 90 minutes, only 90 minutes to go around the Earth. Like if it start from here and it is going around the Earth, so it will get back to same point just in 90 minutes. It shows that they are very, very fast moving satellites. Okay, so now let's look for some terms related to the satellite motion. The first term is orbital radius. Orbital radius means the distance between the satellite and the center of the Earth or the planet or whatever thing is at the center. Let's say here Sun is at the center and let's say Earth is over here. So we say that from center of Earth to center of Sun, this R is known as orbital radius. Well, if orbital radius, at times orbital radius mean radius of Earth to the height above the surface of Earth. This can also happen. Let's imagine this is Earth and this is the radius of the Earth and any satellite is over here. So it is at an altitude of h above it. And we know that the orbital radius is actually distance from center of Earth to that satellite. So that's why I have written that the orbital radius is equal to radius of that planet plus height of satellite above the surface. For the derivation of the expression, we have to use centripetal force equal gravitational force because the centripetal force is being provided to the satellite by the gravitational force. And this is the main expression. Whatever you have to find, like orbital radius, orbital velocity, angular velocity, or time period, you will always start from this expression. And now You know that the centripetal force is equal to mv square over r. We have learned that in circular motion, or centripetal force is equal to mr omega square. So you can use any one of them, but one more thing is omega is equal to 2 pi over t. So instead of omega over here, you can just plug in its value as well. Okay, so mr omega square equal gmm over r square. So this m and m goes away, and you're left with r omega square equals gm over r square. Okay, so now let's get to the main expression for that. Okay, so now as previously we ended up at the last expression of this, so we can carry forward with that. R cube is equal to gm over omega square, and then taking the cube root, you will get the expression. This is the first expression, which is in terms of mass of the planet and angular velocity. The other expression is, as I told you, that omega is 2 pi over t, so omega square would be 4 pi square over t square. So replacing this omega square with its value over there. So you end up with this and then going t square up. So this is the second expression, which is in terms of time period and mass. Now we have to look for orbital speed. What is orbital speed? It is the speed of the satellite in its orbit, or we can say the distance moved by satellite per unit time is known as orbital speed. So I'm talking about this orbital speed. So again, you have to use Fc equal Fg, and then for Fc, I am using mv square by r now. Why? Because I have to find orbital speed v. Then this m is cancelled away, and this r and r goes away. So you're left with v square equal gm over r. You take the square root, and you got the answer. And you can just see that this r is orbital radius. In some cases, that can be radius plus height above the surface. Well, about the orbital time period, it is a time taken by a satellite to complete one rotation. Like you can see that if Earth or this planet starts from here, so you start the timer and it is going around, and when it will get back to the same point over here, we will say this is the time period, the time taken by Earth to complete one rotation. Well, about the derivation, again, this is your core expression, core equation, so you always start from here. And then you have to just plug in their value. Fc is mr omega square, Fg is gmm over r square. By the way, this sun is having big mass, this earth is having small mass, and the distance from center of earth to the center of mass is orbital radius. And omega is the angular velocity. Okay, so this m and m goes away, and you're left with and you shift this r over there. So that's why it is omega square equal gm over r cube. And we know that omega is 2 pi over t. And as we have omega square, so just take it square. So it is 4 pi square over t square. So using these values, we can get the expression. You can cross multiply them, and actually we're working for t, so make t as the subject, and then you can do one trick. You have to take the square root of these equations, but the square root of 4 pi square is 2 pi. That's why it get out of it, and this r cube over gm left over there, or you can keep 4 pi square inside the square root as well. So sometime about the time period, they can ask you to show that t square is equal to cr cube. This is actually Kepler's third law of planetary motion. Planetary motion. Kepler also developed the laws for cube of radius. So they can ask you to prove this as well. or they can, of course, the t square is constant into r cube. So what you can do from here, that you can see that, well, you can see that if you don't take the square root over there, like no need to take the square root. So you can say that this 4 pi square over gm is constant. So that's why you wrote this as constant. So this is constant. And then you can simply say that t square is equal to cr cube, or you can say that t square is proportional to r cube. I hope that will work. So I'm just closing it. Today we have studied about gravitational force. We have studied about Newton's gravitational law. And then we have studied about satellite, what is satellite, what is orbit, what are the types of the satellites, geostationary and polar. And then we studied the terms. The first term was the orbital radius, then the orbital velocity, then the angular velocity, and then the time period. And the main expression for satellite motion was gravitational force supplies the centripetal force, and this centripetal force can be mv square over r, or it can be mr omega square. And of course this is from Newton's universal gravitational law. So thank you, students. I hope that you understood it. In case of any ambiguity, you can directly contact me. Thank you, everyone. Take care.